All right, y'all, let's get at it. Welcome to Get Demystified. I'm Matthew. Happy to be here. Super excited about this talk. I'm gonna get real nerdy, so I hope y'all can keep up. A little bit about me. I am currently living in Denver, originally from Chicago. Moved there back in like March 2020, right when COVID hit. Good timing. I stayed in Chicago for a degree in computer science at UIC. Lived here my whole life up until a couple years ago.
And I got sure.
Started playing with Drupal back in 2012 when I was in college. My first Drupal website was for the LGBTQ group in college. Back on Drupal 7. That was painful. I'm currently a lead developer. I love DevOps. I have a Linux tattoo. I play with Linux all day. Love being in the command line. And I have a disability called cerebral palsy. Obviously, it makes it hard to talk sometimes when I get excited. So if you have any trouble understanding me, let me know, and I will calm down, hopefully. I work at Bounteous. Bounteous is based out of Chicago. We're a digital consultancy. We work directly with our clients, co-innovating. We do everything from technology, Drupal, AEM, to design, marketing, UI, UX, all that fun stuff. Yeah. I did put some links to the slides. There's going to be a lot of code in this talk. So if you want to follow along with the code, you can hit that link. It's also in the session description. There's a shell file that you can look at on GitHub if you want to come back and look at this stuff. So what we're going to talk about today, I'll give us a little bit of an intro to Git, what it's for, how to get it initialized, and then I'm going to talk about Git objects, which are the brain of Git, how it tracks data, how it remembers your information, and then I'll get into some Git commands and talk about how those commands are altering your working tree and keeping track of your history. So that being said, this is a really technical talk. I'm going to get into the weeds, talk about what's happening under the hood in the world of Git, and previous use of Git is helpful. It's not required though. Hopefully, if you're not super familiar with Git, there'll be a couple of spots for questions. Happy to fill people in if you get lost. And then as far as these slides, there's going to be a lot of code on these slides, so I tried to make it a little clear about what's happening. So the commands that I'm running are going to be uncommented. The output from those commands will be commented for clarity. So the green text is just the output from whatever we're running. And all this is in the shell file if you want to take a look at it now or later. So that being said, let's get in the groove. I promise you this is the only pun in this talk. Wink, wink. So Git is an open source version control system used to track code over the history of your project, track changes and files over time. It was created in 2005 by Linus Torvalds for the development of the Linux kernel. It's really not that old. If that name sounds familiar, that's the guy who created Linux, and he created it for the development of the Linux kernel, to keep track of those changes over time. There are like other version control systems out there, like SVN, that people can use that are a little bit older. It's used really heavily by the Drupal project to track changes to Drupal. So, if you've ever looked at the current code, open a pull request for anything in Drupal. You're working in GitLab currently. That's obviously driven by Git. So used really heavily in Drupal. And it's the most widely used version control system currently. I think I saw something like 70% of projects are currently using Git to track their development. So, a little bit of the basics about how Git works. So I grabbed this image from Git has really good documentation online. This is one of their diagrams. So when we're working in Git, wrong button. So you have your working directory, you're making changes to code, all that is great. When you're ready to finalize your changes, you're going to add them into a staging area, so kind of a middle area between your working directory and then the history of your project. So once you're ready to finalize your changes, you will commit them to your repository, at which point all the changes you made are put into your .git directory and stored there for everyone to use. Makes them permanent in your history. So if you remember the old Drupal 7 days, or if you've ever done a pull request review, this might look a little familiar. This is a diff. It shows you what line was added in green, what line was taken away. It communicates to us how a file has changed over the course of our repository. And really what I want you to take away from this talk is that Git stores snapshots. It does not store diffs. So that's not how Git thinks. It's not what Git is doing. It's just how it communicates to us what has changed over time. So when we create a repository, we use the git init command, and we can take a quick peek. So on the right here on line 9, I'm creating a new repository. I list out the repository. We see a bunch of files here. The first one, that config file, is our information about our remotes and our branches. So whenever you do like a git push or a git pull, you're sending and receiving code based on what's in that config file. We're not going to talk about that too much. Likewise, the head file here represents your currently checked out commit. So whatever commit is currently active in your working directory is referenced in that head file. It's how Git knows what the changes are in comparison to your current environment or your current working directory. And then Git index. The index file is a single file. It's our staging area. Whenever we do git add or we're adding stuff to our staging area, it's actually putting it in that index file and updating it. We'll show how that works. And then objects, we're going to spend a lot of time talking through, kind of like the brain of Git. It's how it's actually remembering what files have changed and what the state of your data is at any given moment. So anytime you make a change to a file and commit it, it's going to end up in that objects directory. And then refs are pointers to Git objects. And we'll see what those are for. So all objects, we're going to focus in on objects, talk about objects for a little bit. All objects are identified by an object ID, also known as a hash. Git gives us this really cool command where we can actually calculate the hash of a given string. So on line 26 here, we're giving it the string hello world, pass it into hash object, which is a Git command that will take that data, give you the hash for it. The -w flag means create this as an object in your database. So if you do that with our hello world string, we have this commit, or this object 557db0. That's something I'll be referencing for these first slides. We can actually see that object as a file in our file system. So it'll be stored at .git /objects/55/ the rest of that hash. And we can also get the contents of an object using the cat file command. So the -p says, pretty print out this object. We give it that object ID, and it gives us that hello world string based off of that hash object function that we just ran. These hashes are SHA-1. Newer versions of Git, depending on your configuration, might use SHA-256. A SHA-1 hash is 160 bits long. In hex, that equals 40 characters. So you will see, the length of that hash that we're given is actually 40 characters. And we can reference those objects by a partial hash. So, we can either tell the cat file our whole object. We can reference that object by 557db0. We can also reference it by just 557d. As long as you have a unique string in the front of your reference, it'll find it. So as you have more objects in your database, you'll have to add more characters to that hash to identify it as you're referencing it. A lot of the time on like GitLab and GitHub, you'll see that 6-character hash. So that's what I'll be talking through or referencing when I'm talking about this hello world hash or object. So objects really are the brain of Git. I did, just listing out our objects directory here after a few commits. You'll see we have like 7 different objects. They're all different types of objects. So, all hashes are stored as a file. You'll notice that there's not any file extension on these. So if you're adding, the readme.txt file to your project, it's not going to store that as, .txt in the objects directory. It's just going to store it with whatever the hash of that object is. And there are different types of objects. We're going to talk through each of them and how they reference each other. We'll see there's blob objects, which are a file. There's tree objects, which are a directory, and commit objects, which are a commit. Let's see how these come together. So, starting with blob objects, a blob object is the contents of a file. It is only the contents of a file. And it is a snapshot in time. It is not a diff between one commit or another. It's going to be the entire contents of a file at a specific point in time. You're also not going to see any metadata in a blob object, so you're not going to see file permissions, you're not going to see file name, you're just going to see the contents of whatever is in that file at a given point in time. So we have a single file, whole file, nothing but the file. So help me, Raman. Plus some, additional Git stuff that helps us identify what that object is. So that 557db0 hash is not the hash of hello world. It's the hash of hello world plus some additional data that tells Git that it is an object. We're not going to worry about that too much. And then blob objects get created when you run the git add command. So let's see what that looks like. Git add, we have our staging area, we have our working directory, we're making changes in our working directory, we're ready to turn them into a commit and then add them into our project. So I'm going to take that hello world string, put it into readme.txt, run a git add on that file, and run a git status to see, the current status of whether or not things are in our staging area ready to be committed. So we'll see on line 52, we have, it's saying we have a new file that we're adding, and, tell us what our next commit is going to look like. So if we take that hello world string that we know the hash for, put it into a readme.txt file, Git gives us this really cool command called ls_files-stage. This prints out the contents of that staging area, which is stored in that index file. So we'll see now we have file permissions and metadata. So that first part, we have our, so we have our permission bits. We have the object ID that file is pointing to, so it's our hello world string. We have a flag after that hash that tells us the conflict status of a file. So we'll see how that shows up in the future. And then we have the file name. And again, this blob is a file on the system at get objects 557db0, which has that hello world string. So when we're ready, staging area can have multiple files in it. So if we make a directory called docroot, take that same hello world string, put it into index.html, run that same get ls files, we will see that we now have two files in our staging area, readme.txt, index.html. They're both referencing the same blob because they have the same data in them. So you can kind of start to see here how Git does some magic to save space and save calculations as it's determining the staging area code. So if we take that staging area, we can turn it into a commit, add it to our Git history via the git commit command, and we'll see some output that tells us what Git just created. So we have we have a list of changes. We have two different files here. One is readme.txt, one is index.html. But we also get this fancy object. So when you run a commit, it's also creating an object in your objects directory. And that commit object is what identifies the history of your project. So again, we can take the hash for that commit object. So ECBD, I made that really hard to say for me, which is awesome. We can run that same git cat file command, see what the contents of that object are. We get something like this. We have our committer information. We have that commit message that we just added. It tells us what this set of changes represent. And then we also get this really cool tree object, which is another object with a different hash. And if you take a peek at that tree, or at that object, again with the cat file command, we'll get something like this. And this is where we start to see metadata about the history of our project. So we can see that this tree object is pointing to our 557db0 blob via readme.txt. But then we also have another tree object pointing to docroot. And again, we can go a level deeper, take a look at that object, and we see our index.html file pointing to 557db0. And that ends up looking something like this. So at the top there, we have our commit object. That commit object is pointing to a tree. That tree object is pointing to a blob, as well as another tree, and that other tree references a blob object. So this is how Git represents data in your project. Whenever you're looking at a commit, it uses that to determine what the exact contents of your code at that point in time. So I'm gonna pause in a second, but I wanted to add a little bit of complexity before I do that with a second commit. So if we take a different string, git rules, put it into readme.txt, run that same git add ls files -- stage, we see something a little bit different now. So the hash for readme.txt has now changed. It's pointing to a different blob object. we still have our doc.root/index.html file in our staging area, even though it hasn't changed. So whenever you do ls files dash stage, it gives you the state of every file in your code and the blob that it points to. So if we make a second commit with that get ruled string, we'll get into the commit object. If we take a peek at that commit object, we have our same commit information, as well as a different tree that we're pointing to. It's a different tree because it's pointing to different files with different content. So you can see on the left here, we have an additional tree. That tree is still pointing to our old hello world blob via the doc root tree. So it's still pointing to that old tree, but it's also pointing to a new blob via the reading.txt file. So this is how Git is representing data under the hood. It's how it determines the state of your code at any given time. It's not remembering what has changed. It's just remembering the snapshot of a file at a specific point in time. So I'm gonna give you all a second to catch up. I know this is a lot I just threw at you. Anyone have questions about this first part? We're gonna hop into merging work streams together, Git rebase, all that fun stuff. But this is kind of the setup for how we're thinking about what Git is doing. Yes?
String first. I might have misunderstood. Did you say that when you ls files in stage, it shows you the current state of every file in the project?
Yeah, so git ls files dash stage shows you every file in your project, regardless of whether or not it has changed in your current commit or if you've added it to your staging area.
So there's a flag on one of those if it is actually staged.
Yeah, it just looks at that blob. So it doesn't know whether or not a file is different. It's just pointing to that blob object, and it'll look when you do a commit and compare it to the previous tree and tell you what has changed.
Gotcha.
Any other questions? This is fun. So let's look at branches. Who wants to guess what a branch is?
A tree.
No. So sorry?
A deviation?
It is not a deviation. A branch, I'll set up a little bit of a scenario here. So, leaving our old commits behind, I'm going to simplify things a little bit, give us a new tree. So we have our root commit at our main branch on the left. The squares are our branches, circles are commits, and then we have two separate branches here. Branch A that says Git sucks, and a branch B that says Git rules. We can take that branch object and see what it is. And branch objects are stored in .git/refs. They are not objects. They are just pointers to objects. So you don't need to do git cat file. You can just cat out, print out the contents of that file. You'll get whatever hash that branch is pointing to. So branch A is pointing to commit C. Branch B is pointing to commit E. So Git doesn't care what branches are. And likewise, we can create new branches. We can also create tags, which are both references to commit objects. The difference between a branch and a tag is that a branch can be changed. A tag cannot be changed. So branches are mutable, tags are immutable, but they're both stored in the same way. So a tag, will point to commit D. We can tell it to create a tag or a branch at a specific point by doing checkout-b or tag and giving it that commit hash. Git will go look up that commit hash, make a new reference object, and put a pointer to that hash in that file. We got. So I'm going to talk about merging and combining these two work streams. So we have two different work streams and a few different ways to combine them. So we're going to work on combining, branch A and branch B. We'll talk about merging, which is on the left. We'll talk about rebasing, which is in the middle. Everyone has fun with that. And then we'll talk about how cherry picking works as well. So let's start with a merge. If we check out branch B, we're on branch B. We want to merge branch A. You can run git merge branch A, and since those two branches both have changes in the same file, we get a really fun merge conflict that everyone loves, right? Maybe. So what's actually happening when you run git commit, merge? So git does what's called a three-way merge between these two branches. It starts by finding their common ancestor. So branch B, we have two commits after commit A. Branch A, we have two commits after commit A. It's going to go back through our history, go through each one of those commit objects, find the parent until it finds two parents that match. So it grabs that, and then it runs a diff. So diff is what we saw in that patch file. It'll compare the content of commit E to commit A and give us that as a diff. And it'll do the same for commit A and commit C. And then we get two separate diffs like this. So, git diff allows us to run that same process and C. Kind of looks like a patch file. If we do git diff A to branch B, we'll see that we're adding the string git rules. If we do git diff A to branch A, we'll see that we're adding git stinks. And there's a little bit of information about here about like the file that changed. It's gonna look and see that the bytes in these two files that changed, the lines, the lines in these two files changed, which is why there's a merge conflict. So, if there's not a conflict, it'll pull in the changes from both sides. If there is a conflict, it'll yell at us and tell us that we need to fix it. So when we're in this state, if we actually take a look at the readme.txt file, we'll see something that looks like the following. Might look a little familiar to you. And this is telling us that, in our current commit, we have git rules. In the branch that we're trying to merge, we have git sucks. And it's up to us to come in here and actually update this file and put the correct contents in it. So you can either do that via an IDE, an IDE. Some IDEs have that built in where you can resolve conflicts. You can also just go and update the file directly and change it to whatever you want it to be that is correct. It's also possible to commit this without updating anything, in which case you'll break all your stuff. We won't talk about that. What I think is really interesting though is if we take that same git ls files -- stage, we'll see we now have the readme.txt file listed 3 times. And we have that merge conflict indicator set. So the first line is our object for our A, so that hello world string 557db0. We'll have branch B, so the representation there, which is git rules, and then branch A, which is git sucks. These are all running that same hash object to get the contents of that file. So this is how Git knows that you're currently in a merge conflict. It looks at this index and it says, I have these files flagged as conflict, and it'll also update that file to show what the conflict is. So if we were to just put whatever content we want, resolve those conflicts, I'm going to put git rules, run that same git add command, and ls files -- stage, we'll see that we no longer have those 3 entries because that conflict has been marked as resolved. So we're back to our normal state where we just have a blob representing whatever is in the contents of that file ready to be committed to our repository. So when we resolve that conflict and run git commit, we're given another commit hash. So in this case, we're at commit F, which represents our merge between branch A and branch B. Again, if we can cat out that object, we'll see that we have a tree object that it's referencing that tells us the state of the files. But then we'll see that we actually have 2 parents instead of 1 parent. So this tells us that, this commit came from these 2 places. And there are actually ways to merge more than 1 branch at a time. There's different algorithms for merging. If you really wanted to get crazy, you can have however many parents you want in there, however many branches merged together at once. So that's merge. Let's talk about rebase really quick. So rebase is a really fun one. The difference between merge and rebase is that in a rebase, you're not making a merge commit. You're copying history from one branch to another. And the way it does this is, again, it'll find that common ancestor, and then it checks out the branch that we are rebasing onto. So branch B moves from commit E up to commit C. So at this point, we're just starting our rebase. Both our branches are pointing to the same place. And then it runs through that diff process again. So it's going to compare, instead of comparing commit E to commit A, it's going to compare commit A to commit D. So, gets that diff instead of, across the whole change set. It's just going to do 1 commit at a time. So it gets that diff, and then it adds it on to the end of branch A and updates our branch B pointer to have that. And it'll use the same commit information, so you'll see the same author, you'll see the same commit time, and it'll be pointing to a different tree. And then it'll repeat that process for the next 2 commits. So it's going to take commit D, compare it to commit E. We have that get rule string. When we apply it to branch A again, or current branch B, it'll move our pointer forward. We're also going to get a conflict here, and it works in the same way. So we're rebasing, we have a conflict between our 2 changes, it'll yell at us, we have to go in and update that, and make sure that resolve the conflict, run git add, rebase continue, and it'll continue on with the process. So difference between merge and rebase is merge combines everything to 1 commit. Rebase takes those changes and puts them on top of another branch. But what's really cool here in this diagram, flashing git, is that those old commits are still there. They're still in the object directory. They don't go away even though our branch isn't referencing them anymore. So if we want to, we can move branch B back to where it was via the git reset command. So we took it from E prime and moved it back to E, and now branch is pointing to commit E again. Likewise, our rebase commits are also still in history. So if we wanted to, we can move it back and forth. Git doesn't care what that branch is. It just knows that branch is pointing to a specific commit. So we can move it around, put it wherever we want. And if we do something that we don't like, we can always go back in history and find the old objects that it used to reference, update that pointer to the old objects. And you can do git reset hard, git reset soft. The difference between hard and soft is hard will get rid of your changes. Soft will just update the pointer, but it won't reset your changes. So you'll still have that same working directory, you'll still have that same tree, you'll have the same blob objects, it's just pointing to a different place. I'm not going to jump into that too much, but let's take a look at cherry picking. And of course, I'm like flying through this, but so if we wanted to cherry pick that commit, the difference between a merge is combining two trees. A rebase takes a tree and puts it on top of another one. A cherry pick takes a single commit and puts it somewhere else. So if we were to cherry pick the E commit from branch B to branch A, again, it's going to take that diff between E and its parent. It's not going to go back to P. It's not going to compare anything beyond that. It'll just compare commit E to commit D, get a diff between those two things, and then put it at the end of your branch. And in this case, I'm cherry picking, a commit onto branch A, so I'm not doing it onto commit B. But it will, you'll run into those same conflicts because the strings are different. The same file changed, and then you will have another commit with a new tree with the new contents of that file pointing to on top of branch A. So that's how cherry pick works. And of course, what's really interesting is that since Git sees these two commits as, they're two different objects, they have different parents, they'll have a different hash, you could actually cherry pick a commit twice. So we cherry pick E, cherry pick E, we'll have it on branch A. We could actually cherry pick that again, and then we'll have it in our branch A twice. And again, we'll have to resolve conflicts. It might yell at you and say nothing has actually changed when we do this, because it's actually in the same state of code. But point being that Git doesn't really care, what your objects are. It doesn't care where your branches are pointing. All it cares about is the state of your code in that time and how to get from one commit to another. So, in summary, that's fun. So Git, file-based version control system. There's other version control systems. It uses objects and then references those objects to determine the history of your code. Branches are refs. They're just pointing to objects. They don't care what's actually on that branch. They're just references. Git stores an entire snapshot of a file. So when you go from one commit to another, it's not saying, oh, this line was added here. It's saying, this is the exact state of my code at this point in time in the commit. Commit objects, there's three types of objects. Commit objects point to tree objects point to blob objects. And that's how it's determining the state of things. Branches are pointers. Git doesn't care what they're pointers to. So it's a really interesting, technology. I always thought it was like remembering the diff between various commits, but it's not actually doing that. It's actually remembering, the exact state of your code at any given point in time. And that's what I got. There's my other pun. Let's get at her. That was a lot. I can go back if people have questions. I think I can. If there's certain things that you all want me to touch on, talk through. What's up, Bob?
So, you've got multiple people working on a team, you're committing everything, and you end up with conflicts coming from different branches.
Yep.
And what would cause it if you have duplicate commits showing up in your changes?
Yeah, so if we go back to
What
that.
would cause that?
Yeah, so if we go back a couple slides here, how do I do things? So in this example, not this example, not that one, that one. So, so this is an example of having a duplicate commit. So, we cherry picked E once, we'll have that, on branch A. If we cherry pick it again, it'll be there duplicated. Git's not gonna say that like they're the same thing. It's just looking at them as two different objects in your history based off of like what you told it to commit, whatever the parents are, and it's just gonna know those state of the files at that point in time.
So if you get those duplicates when you haven't been using cherry pick,
Yeah, it can come from.
because you've got maybe two parents out there,
It could come from like if you merge a branch, or I guess it depends. So if you merge a branch twice, it won't make that duplicate commit. It'll just have that like pointing. It'll have a merge commit. But if you're rebasing or something, you could end up with those duplicates. I think you can. Well, no, you can't rebase the branch on itself, but if you were to rebase the branch twice and then cherry pick or do something weird with merging, you can definitely end up with duplicate commits. Git doesn't know they're duplicates though, it just thinks they're different commits. They might be pointing to the same tree object, but they're gonna have different parent objects. So Git's gonna see them as two different things. And you can actually, you can rewrite that history. So, like we did with the git reset command. Where'd that go? No, yeah. So if your branch is pointing to commit E prime, double prime, and it's, if we have a duplicate commit there, we can say, hey Git, take this branch pointer, point it to an earlier point in history, and you'll have just that single commit at whatever time. Your duplicate commit is still going to be in your object database. It won't push it up to your repo if there's not a branch pointing to it, but you're still going to have that old object. Git doesn't care where your branch is pointing; it's just pointing to a specific commit in time. Cool. Other questions? Yeah.
Does squash, when you squash commits,
Ooh,
does it remove the references?
Yeah, so a squash, what it does is it will, I guess it would just grab the tree of the last commit, because it doesn't care like what the commits are. It's just gonna look at that tree object. So when you squash, it's gonna make a new commit pointing to that same tree object with whatever kind of squash message you want, and you'll still have your old commits that you can go back and reference, but it cleans up the history so that you only have a commit object, a single commit object versus multiple.
So the objects still exist, but it just cleans up the commit
Right.
history. So
Yeah.
Two different things.
Yeah. So
Objects are not history.
yeah, exactly.
let's get stash work.
That's it. A good question. I don't know. But my guess would be, when you're stashing, it's probably going to make another object in your database, and add a reference somewhere to it. So like maybe I could imagine like, when you do a git stash, it makes a new tree object, puts that tree object in your object database, and then probably adds a reference somewhere to, say when you want to pop it, apply this tree to the current working directory. So kind of like checking out a commit. Next. Yeah.
How do you choose between like a merge or a rebase?
Yeah. Yeah, so the question is, how do you choose between merge, rebase, cherry pick? So typically a merge is when, your work is coming together. So when you open a pull request, you're gonna merge two branches together, and it'll have that new tree. When you're doing a rebase, you know, typically that's when, you know, if you're working on something locally, you've made a lot of changes, but your, you know, the upstream like branch has changed or something. You want to take all your work and put it on, you know, that other branch that has all your other changes in it. And then cherry pick is if you only want one change that you made in your history, it'll take that one change and put it onto the branch. Does that answer your question? Okay, cool. Whew. Anyone else?
So when you're doing a get pull, it's gonna grab your, whatever your origin branch is, right?
Yeah.
And it will fetch it, and it will merge it.
So when you do it,
So there's also the option to set it up to rebase all the time?
I don't know if you can pull. Actually, I think you can pull rebase, but when you do just like a regular git pull, it'll treat it like a merge. So, you know, if you have changes locally that are different than what's upstream, it'll merge those two together, make a new merge commit. It actually allows you to like update that commit message. What was I gonna say? Yeah. That was, yeah.
Occasionally, we've been getting a message saying that you, what does it say, actually? It's saying that you can set it up to automatically rebase every time you do a get pull.
Yeah.
With your merge, or, well, pull, merge and rebase, I guess it is, right?
Yeah.
It's doing both of those things, or not.
Yeah, so default is merge. You know, when you do a merge, if your two branches are coming from the same place, so like if you have changes locally that are on top of whatever is remote, and you do a git pull, it'll do what's called a fast forward. So instead of making a merge commit locally, it's gonna do more of like a rebase where it will take those commits and just, you know, apply them on top of whatever the remote branch is and update the pointer to whatever that latest commit is.
I think this comes up usually when we're running into conflicts on that pull.
Yeah, so you know, merge conflicts. It's going to, you know, look at those two commits in history, find the common parent, and then let's see, where is it? How does it represent that? And do that same diff process between the two. Oh my God, commits. And that's where like you get a conflict if, you know, something upstream has changed, something in your branch has changed. It's gonna do that same merge process. See that there's a conflict. It'll pause so it won't, you know, complete the merge and make a commit. It'll give you a chance to resolve those conflicts, and then you can commit directly. Cool. Anything else? Was this helpful?
Very helpful.
Awesome.
Yes.
Love it.
So most of these presentations that I've seen don't go into what Git does in the background.
Yeah, this is a lot
Really
of
helpful
fun.
in kind of figuring out what is it doing and why am I
Yeah.
having this problem.
Yeah, exactly.
Yeah.
It's,
I like it.
yeah, and then, I mean, like I said, I was really surprised that it's not like storing diffs.
Yeah.
It's just storing whatever the exact state of your code is at any given time.
That seems so surprising, or like counterintuitive, because
Yeah.
it seems like that would be more, you know, expensive than SVN, which did store diffs, right? Is that how they did, or?
I didn't look. I think SVN is also snapshot based. I'm not sure.
It
Well-
makes sense though, because otherwise you'd have to compare tons of diffs, like commit A, commit
Mhm.
B, commit C, and you'd have to store the diffs for each
Right.
variation of that, so a snapshot makes sense, and then you just run a function or something
Sure.
to get the diff.
And
So that kind of makes sense.
The
Yeah.
contents of the files are stored as hashes, not. like-
Yeah, as blob objects with a specific hash. Yeah.
I have a question, kind of back from earlier, one of the first commits, where you're pointing to like the blobs.
Yeah, Mr. Hagen. over here. Love that. I'm just gonna leave that here.
Yeah, and the main question I had was you had both the reading of text and the index of HTML pointing to the same blob.
Right.
And I was wondering why. Like, I don't quite understand that.
Yeah, I can get to that really quick here. Oh, technology. Oh, there it is. So yeah, in our last commit here, yeah, they are pointing to the same blob, right? We had two different files, and that's because those two files both have the hello world string in them. So the hash, you know, a blob object is just the contents of the file. It's not going to store like the file name or the permissions or anything. It's just the literal contents of that file. So since those two objects or those two files have the same content, they have the same hash. So they point to the same place. This one.
Not often going to happen. It's kind of an edge casey sort of thing.
Yeah, but like, you know, as you're updating history, you know, it'll still point to that old object, right? So it's going to keep that, you know, if you were to, you know, revert a file in the future, it'll point back to that old blob because they're the same file contents. Cool. Any other questions? Awesome. Well, thank you all. This is a lot of fun to make. Hope it was helpful.